Hello, today we're continuing in our series on GCSE Physics, looking at Newton's laws of motion. There are three laws. The first says that a body continues in its state of rest or uniform motion unless acted on by an external force. What does that mean? Well, that means that if you take a body, like a car, and you put it down at rest, it won't move unless a force acts on it. That sounds pretty plausible. If I want it to move, I've got to give it a force and then it will move. But the second part of that law is not quite so obvious, because what Newton says is that if you give that car a force, it will continue forever at a constant velocity. But of course, all of our experience tells us that that is precisely what it doesn't do. If I give it a force, it stops. If I roll a ball along the ground, sooner or later, it stops. How is it then that Newton thinks that if I give it a force, it will carry on forever? Well, Newton doesn't say it will carry on forever. It says it will carry on at a constant velocity unless acted on by an external force. And of course, it is acted on by an external force because as this car goes across the cloth, friction is acting between the wheels and the cloth. And that friction is a force. It's a force which is slowing the car down. Friction always opposes motion. So if the car is going in this direction, friction is pointing back in this direction and slowing it down. So actually Newton's law is right. This car would indeed continue forever at a constant velocity were it not for friction. And if you go into outer space, well away from gravity, because gravity, as we shall see later, is also a force that will slow you down or speed you up, depending. If you get into outer space and you get your tennis ball and your racket and you serve the tennis ball at, 100 miles an hour? That tennis ball will continue at 100 miles an hour without any more input from you, right the way across the universe, forever. It will never slow down so long as it doesn't encounter any forces, and that might include gravitational forces, which would cause it to slow down or change direction. So Newton's law. If a body is at rest, it'll stay at rest unless acted on by a force. Or if a body is moving, it will carry on moving unless it is acted on by an external force. And on Earth, we always observe that frictional forces, or air resistance, or whatever it may be, act as a force to slow us down. But if they weren't there, without any need for any more pushing, this car would just continue to travel forevermore, were it not for the fact that friction slows it down. So now we come to the second law of Newton, which can best be described by a formula, and I'll show you what the formula is. If you take a body of mass m and you give it a force, just like I hit the car has a mass m, I give it a whack, that is a force F, then Newton's second law can be written in this form: F equals ma. In other words, a is the acceleration, just as it was in the first video that we did. If you take a mass, you give it a force, it will accelerate, and it will accelerate for as long as the force applies. If you take the force away, then of course there's no longer any force, so there won't be any acceleration, and consequently Newton's first law now applies. A body will continue at the velocity it was for as long as you like until it's acted on by another force. So if you give a mass a force, that will accelerate it. If you take the force away, whatever velocity that mass has reached by the time you take the force away is the velocity at which it will continue to travel forevermore unless it is acted on by an external force. That's Newton's second law. Now we come to Newton's third law, which is sometimes described as for every action there is an equal and opposite reaction. but you have to be very careful about what you mean by that. Let's take a tree. And I am standing here pushing on the tree. Now what Newton's law says, third law says, I push on the tree with a force F. But the tree pushes on me with an equal and opposite force F. So I push the tree and the tree pushes me. There's an equal and opposite force. If I take a table and I put a book on the table, that book will have a mass m. The book exerts a force on the table, and the table exerts an equal and opposite force on the book. Now, some people say, well, if the forces are equal and opposite, how does anything ever move? And you need to be a bit careful here, because you'll notice that the forces do not apply to the same thing. There are not equal and opposite forces on that book. There is a force on the book from the table, and there is a force on the table from the book. So actually only one force is applying to the book, and one force is applying to the table. Here, I am pushing the tree. The only force on the tree is me. The tree is pushing on me. The only force on me is provided by the tree. Okay, you say, well, if that's the case, I thought Newton's second law, which we just derived, said that force is mass times acceleration. If that's the case, if I am applying a force to a tree, why does the tree not accelerate in that direction? And the answer is, well, it would, were it not for the fact that there are other forces in play. Largely the roots. The roots go down in the ground and they are providing forces to stop the tree from moving. That, in a sense, is one of their main points. So yes, if the tree were not rooted to the ground and you put a force on it, then there would be an acceleration which you could calculate, because you know the mass of the tree, you know the force, you would be able to work out the acceleration. So yes, that would be true. And then you say, but if the tree is exerting a force on me, why don't I accelerate backwards in this direction? And the answer, of course, is I would, were it not for the fact that there is friction between my shoes and the ground that stops me from doing it. But if I were on sheet ice and I push a tree, the tree pushes me, you can bet your life I would be pushed backwards. If you go to an ice rink and go to the edge of the ice rink where there may be safety rails, grab hold of the safety rail and push the rail. What will happen is you will be pushed backwards across the ice, because the rail has, just as you pushed the rail pushed you, and that's what will make you go backwards. We said a moment ago that gravity is itself a force. If you are standing on the surface of the Earth, there is a force acting on you, which is a gravitational force. It's what keeps you on the Earth. If you attempt to jump up, you will very soon be pulled back down again by gravity. Now you might ask the question, well, how is it then, if gravity is pulling me down, how is it I don't get pulled through the floorboards? And the answer is that the floorboards themselves are being held together by forces. Floorboards are made up of atoms and molecules, and the atoms and molecules in a solid, like a solid floorboard, are actually held together by very strong molecular forces. And those molecular forces are stronger than gravity, at least on the Earth, thankfully. So consequently, when it comes to the battle between gravity and the forces which hold molecules together in floorboards, the floorboards win, and that's why you don't get pulled through the floorboards. So thankfully you only get down to the ground level because molecular forces are stronger than gravity. But what is gravity? Well, leaving aside Einstein's theory of general relativity, which talks about gravity and which we don't need to know about here, Newton's view of gravity was quite simple. He said that if you take any two bodies, anything you like, that have masses, so we're going to give this mass a capital M and we're going to give this mass a little m, if you have any two bodies, he said, then there's a gravitational force between them, which is equal and opposite, which is equal to G, which is called a gravitational constant, times the mass of the first body, times the mass of the second body, and divided by the distance between them squared. And the distance strictly is to the centres in each case. So the force, the gravitational force between any two bodies is GMM divided by r squared. You don't need to know that formula, but I'm telling you so you can understand where all these things come from. So any two bodies, two people exert a gravitational force, but that gravitational force will be extremely small. You would not notice it. But if you take the Sun and the Earth, those are two massive bodies, and there is a significant gravitational force between them. And indeed, it is that gravitational force which keeps the Earth in orbit around the Sun. It's also, of course, the case that if you stand on the Earth, here's the Earth, and here, this is not to scale, obviously. This is you standing on the Earth. The Earth has a mass, capital M, and you have a mass, little m, and the distance between you is the distance between you and the centre of the Earth, because as I said, you always go to the centre. So that is essentially the radius of the Earth. And there is now a force between you, which is equal to this gravitational constant, which is G, times the mass of the Earth, which is extremely heavy, times your mass, which isn't, divided by the radius of the Earth squared. So that's the gravitational force between two bodies, in this case the Earth and you. I should just say that this business of, say, the Sun and the Earth having a gravitational force acting between them is sometimes called action at a distance, because the two bodies don't have to touch. The Earth is 93 million miles away from the Sun, yet still there is a force acting between the two. And remember, it acts on both bodies. So the Sun is attracted, or is attracting the Earth by this force here, and the Earth also attracts the Sun by the same force. The two forces are equal and opposite. But notice, the Sun's force acts on the Earth, the Earth's force acts on the Sun. So in each case there's only one force acting. So let's think again about you standing on the Earth. Here are you standing on the Earth. The distance between you and the centre of the Earth is the radius of the Earth. And I said that the Earth had a mass, capital M, you have a mass, little m, and that the force that acts between you, the gravitational force, is this gravitational constant G times the mass of the Earth times the mass of you divided by r squared, which when you're standing on the surface of the Earth is simply the radius of the Earth. Now observe, this capital G is a constant. It's a universal constant, it never changes. The mass of the Earth, for these purposes, doesn't change, and the radius of the Earth doesn't change. So Gm over r squared are all, for these purposes, constant. The mass of the Earth, the radius of the Earth, and the gravitational constant do not change. And so you can calculate one single value to represent all of those things. And that we call little g. And so now we say that the force is equal to m times little g. So the force acting on me, according to by the Earth, the gravitational force by the Earth is equal to my mass times this little g, which is the combination of these three values here. And on Earth, provided you are at or about the surface of the Earth, G is equal to 9.81 meters per second squared. That is on the surface of the Earth. If you go high above the surface of the Earth, G will reduce. Why? Because R increases. And if R increases, the force decreases because R is in the denominator. So as R gets larger, the force gets smaller. But provided you're round about the surface of the Earth for the first 100 meters or so maybe, you can use this formula, F equals mg. So what we're saying is that when you're standing on the surface of the Earth, there is a force acting on you which is equal to mg, and that is the gravitational force. And we have a name for that. It is simply called weight. So your weight is essentially the force, the gravitational force that acts upon you. And now you can, I hope, see the difference between mass and weight. Your mass doesn't change in any circumstances. Your mass is essentially a measure of the amount of stuff in your body. But your weight critically depends on the value of G. Now on the moon, G is equal to 1.6 meters per second squared. It's about a sixth of the gravity of Earth. Why? Because although G is a constant, the mass of the moon is very much less than the mass of the Earth, and as it happens, the radius of the moon is very much less anyway. But when you take all these figures into account for the moon, you only get 1.6 meters per second squared. So your weight on the moon, the gravitational force acting on you, which we call the weight, is equal to your mass, which is unchanging, times G, which is only a sixth of what it would be on the Earth. So for those of you who are fed up with diets, here is a way to weigh only 1/6 of what you normally weigh. Simply go up to the moon with your pair of scales, and hey presto, you will find that you weigh only 1/6 of what you weigh on the Earth. I'm afraid it's not a very practical proposition, but it would indeed work. So weight is the combination of your mass and this value G, which for the surface of the Earth or close to it is 9.81 meters per second squared. So now I want to go back to this business of taking a mass and applying a force. So there's the mass, I apply a force F, and according to Newton's second law, F equals ma, the body should simply shoot off in this direction with an acceleration a. But of course that's not, unfortunately, all there is to it, as we've already seen with the demonstration of the car. Because when you apply a force on this mass in this direction, there will be a frictional force which will act in the opposite direction. Friction always opposes motion. Not only that, but if you build up any speed, you'll find that there will be quite a significant air resistance, because there's air here. Unless you're in a vacuum, there's air here, and that air will form a resistance to you moving. So what you actually find is that as you push in this direction, there will be a resistive force in this direction. That resistive force combines friction and air resistance and anything else, in fact, that might be a problem. So let's suppose we take our little car and suppose it's got an engine, and that engine can supply a force of 1,000 newtons. Newtons are the units of force. Force is mass times acceleration. Mass, of course, is measured in kilograms in the SI units, and acceleration is measured in meters per second. So you might think that force should have the units kilogram meters per second, and indeed that is perfectly legitimate. But rather than that big mouthful, kilogram meters per second, we have come up with a unit which is the same thing, but it's slightly easier to say, and it's called a Newton, named of course after Isaac Newton. So forces are measured in newtons, but if you want the basics, that is equal to kilogram meter per second. But suppose as this car is being pushed by its engine with a force of 1,000 newtons, it encounters a resistive force of 600 newtons. That would be the combination of friction and air resistance. Well, now there is only going to be a net force of 400 newtons. Do you see why? Because there's 1,000 newtons pushing in this direction, but there's a resistance of 600 newtons, friction and air resistance in this direction. So when you take off the 600 from the 1,000, you're left with only 400 newtons. Let's suppose the car has a mass of 200 kilograms. We can now work out what the acceleration will be, because we know that force equals mass times acceleration. So you can rearrange that to say that acceleration is force divided by mass. We essentially just divide both sides by m. What is the net? So acceleration is force divided by mass. What is the net force? It's 400 newtons. Not 1,000, because the 1,000 is in a sense being offset by the 600. So there's 400 newtons divided by the mass. What was the mass? That was 200 kilograms. So we've got 400 divided by 200, and that of course is just 2 meters per second squared. So the acceleration will be 2 meters per second squared. When you are driving down the motorway, or if anyone is driving down the motorway, you might be travelling at, say, 70 miles an hour. You will need to keep your foot on the accelerator, because if you take your foot off the accelerator, the frictional forces and the air resistance will slow you down. So you are providing force to the wheels from the engine. So that means that there is a force in this direction, which is coming from the engine that's driving you forward. But you are travelling at a constant 70 miles an hour. You are not accelerating. If you are not accelerating, that must mean, it can only mean, that the resistive force against you, which is the combination of friction and air resistance, exactly balances the force provided by the engine. And in those circumstances, the net force is 0. And that's why you don't accelerate. When you're travelling at constant speed and your foot is on the accelerator, what you're actually saying is that the engine force, which is driving you forward, is exactly balanced by the resistive force, friction, air resistance, that is stopping you. It doesn't slow you down, because this force exactly balances this force. The net force is 0, and if the net force is 0, then if F equals ma and F is 0, the mass of course is not 0, that was 200 kilograms, the acceleration must be 0. So there's no acceleration, consequently constant speed. Now let's just look for a moment at this business of netting off forces. I said that if you had a force in this direction of 1,000 newtons, and you had a resistive force in the opposite direction, which was the frictional force, remember, air resistance, of 600 newtons, then we could say that the net force in this direction is going to be the 1,000 minus the 600, which is 400 newtons. And that's fine. In vector terms, that's perfectly all right, provided those forces are in the same line or the same direction. You can simply add them together if the forces were acting in the same direction. For example, if you had a cart and you had 2 people pulling the cart, and one was exerting a force of 1,000 newtons and the other was exerting a force of 600 newtons, they're both pulling in the same direction. And now you can say that the total force is 1,600 newtons, adding the 2 together, because they're both in the same direction. So long as forces are in the same direction, you can either add them if they are both pulling in the same direction, or subtract them if they are opposing one another. That is fine. But what happens if you have, say, a block, which will have a mass m, and you have someone pulling on it with a force of 1,000 newtons in that direction, and someone pulling with a force of 600 newtons in that direction? You can no longer simply net off 600 from 1,000. It doesn't work that way. There is a mathematical formula that does it, but at this level, what you normally have to do is to treat this graphically, and you apply the principle tip to tail. That is to say that you take these two forces and you plot them such that the line for the 1,000 and the line for the 600 newtons is to scale and in the directions in which they're pointing. So you might, for example, draw a line for the 1,000 newtons which was 10 centimetres long. Representing 1 centimetre is 100 newtons, so 10 centimetres is 1,000 newtons, and it's in the direction that this is pulling. And you put the tip on it because that's the direction it's going. Now, you go tip to tail. So you take this one here, which is the 600 newtons, and to scale that will be 6 centimetres. You must put it in the same direction, so it's got to be in this direction, and you put it so that the tail of the 600 meters, sorry, the tail of the 600 newtons is against the tip of the 1,000 newtons, tip to tail. So this is now 6 centimetres long and in the same direction, or it should be, as this one here. Then all you do is you join up the tail of the first to the tip of the last in a straight line, and the length of that line is the resultant force of the two, and the direction of that line is the direction in which that resultant force will act. So in other words, what we're saying is, and it's acting in this direction, what we're saying is if you had 1,000 newtons being, a block being pulled 1,000 newtons in that direction, 600 newtons in that direction, what it would mean is that the block would actually move in this direction with a force that is calculated by the length of this line to scale. So for every centimetre of this line, whatever you measured it to be, that would be, for every centimetre, of course, would be 100 newtons. So you multiply the number of centimetres by 100, and that gets you the resultant force of this line here. So let's do it just to illustrate. We had the 1,000 newtons as 10 centimetres in the, as it were, horizontal direction. Put the tip on like that. We then had the 600 newtons was in, I think, this kind of a direction. Tip to tail, like that. So this is 10 centimetres. This is 6 centimetres. And then I said, to find the resultant force, you just have to join up the tail of the first to the tip of the last, that this is the direction of the resultant force, and the length of the line, I can tell you, is 7.5 centimetres. And since every centimetre represents 100 newtons on this scale, this means that the resultant force is 750 newtons in this kind of southeasterly direction. Let's now consider what's called terminal velocity. If you were to jump out of a plane, and I don't personally recommend it, here you are jumping out of a plane. We know that there is a force acting on you. It is the gravitational force, and that force is equal to mg, as we've shown before. Your mass times the gravity value g, as long as the plane is not too far up. If it gets too far up, g will vary, because g will get smaller the higher you go above the Earth. But as long as the plane is not too far up, this is going to be okay. And what this implies, of course, is that you are going to accelerate with a value g, because g is an acceleration. So what you will do is you will just continue to accelerate, get faster and faster and faster and faster, until of course you finally hit the earth. Now in practice that actually doesn't happen. What will happen is that you will get to a speed or a velocity downwards of approximately 120 miles per hour, and then you won't get any faster. Why don't you get any faster? Because the air resistance, you're falling into the air, and the faster you go, the more air you have to displace. And when you get to 120 miles an hour, the resistance of the air matches the force that's pulling you down. So there is an equal and opposite force, air resistance force, which matches the force of gravity pulling you down. Consequently, the net force is zero, and if the net force is zero, there is no acceleration because F equals ma, and if the force is zero, the acceleration is zero. So once you get to 120 miles an hour, you don't go any faster because the combination of the force pulling you down and the air resistance which is opposing that balance out. So you just continue to travel at what's called a terminal velocity of 120 miles an hour. I guess it's called terminal for two reasons. First, because it's the final velocity you get to. You don't get any higher than that. But I guess it's also called terminal because at 120 miles an hour, if you hit the ground, you don't stand much chance. And that's why, of course, if you're sensible, you don't jump out of the aircraft at all. But if you insist on jumping out of an aircraft, it's always a good idea to have a parachute. Because if you have a parachute, you've still got the same force, mg, pulling you down, but now you've got a great big canopy that is causing a huge amount of air resistance. And so very quickly, the air resistance will get to an amount that it fully matches mg. And it will do that when your speed is about 15 miles an hour, as opposed to 120 miles an hour. Because there's so much more resistance, there's going to be a lot of force resisting you from falling downwards. And very quickly, the downwards pull of gravity will be balanced by the resistive force of this huge canopy. And that means that you will fall down at a terminal velocity, because once these two balance, there's no further force, so there's no acceleration, of about 15 miles an hour. And provided you bend your legs when you hit the ground, I'm no expert at this, so take no advice from me on the practicalities. But at 15 miles an hour, as long as you do it properly, that can be a safe landing. The important thing about all of this is that if the net force, once you've taken the force that's going down and the force that's, as it were, resisting you, if those two forces balance out, if the net force is zero, there can be no acceleration. And what Newton's first law tells you is that if there's no net force, then the object will either stay stationary, unless you put a force on it, it stays stationary, or if it's moving, it will continue moving at a steady speed until such time as something happens. And in this case, either way, you will continue moving at the steady speed of 15 miles an hour if you've got a parachute until something else happens. And of course what happens is you land on the earth and then new forces come into play to stop you travelling any further. So if the net force is zero, there can be no acceleration because F equals ma. Contrariwise, you can say that if you are travelling at constant speed, if you want to speed up, or if you want to slow down, or if you want to change direction, you need a force. Otherwise you can't. To speed up, you probably need an engine to make you go faster. To slow down, you probably need a brake to make you go slower. And if you need to turn a corner, well, you need some kind of force that's going to make you do that. And we'll see what that is in a later video. But I just want to finally look at stopping distances. Let's suppose you are in a car, travelling at a certain speed, v, in this direction, and suddenly someone walks out in front of you some way ahead. And the question is, how do I know whether I will be able to stop in time before hitting them? Well, there are two aspects to this stopping. The first aspect is that you need, first of all, to register that someone's walked out in front of you, and then you need to transfer your foot from the accelerator to the brake. And that will take time. Hopefully not too much time, but it does take time. And in that time, you will travel a certain distance, because you're travelling at speed v, and in a certain time the distance you will travel is going to be the speed times the time. So however long it takes you to register that someone's crossed the road or has stepped out in front of you and you need to do something about it, and actually moving your foot from the accelerator to the brake, that time will determine the distance that you travel before any braking takes place. And that is called thinking distance, because you are going to travel a certain amount of distance whilst you actually work out that something needs to be done. Then you apply the brake, but of course the car will not stop instantaneously. You've got to go slower and slower and slower until you eventually do stop, and that's called the braking distance. So when you need to stop, you're going to have two sets of things to think about, or you don't think about them, it should be automatic. There'll be a thinking distance where you're not slowing down at all, and then a braking distance where you're relying on the brakes to help you to stop. So what is going to affect these things? Well, let's first of all think about the thinking distance. You are travelling at a certain velocity, so whatever your speed or velocity is, that's that. There's not a lot you can do about that, though obviously the slower you are travelling, the less distance you will cover, as we shall see in a minute. But the critical thing in thinking distance is the amount of time it takes you for that thinking to happen. It should be something of the order of half a second, but that time will increase if you are tired, if you're not paying attention, if you've been drinking alcohol, if you're under the influence of drugs. All of that will make that time a longer time. And if that time is longer, so is the distance that you will travel before you even think about applying the brake. That's the reason why you need to be fresh and alert and not under the influence of anything that might distort your ability to quickly react. What will affect the braking distance? Well, the state of your tyres. If they are not in a very good state, you might skid. The state of the road. If it is wet, you're more likely to skid, or at least the friction will be less, because it's the friction between the tyre and the road that is going to achieve the braking. And finally, of course, the quality of your brakes. If you haven't had your brakes checked and replaced, they might be loose or faulty, and they don't give enough grip to the tyre, and they also slow down the time at which you can brake. The Highway Code in the United Kingdom gives illustrations of the distance you travel before you can safely stop for different speeds. 30 miles an hour, 50 miles an hour and 70 miles an hour. At 30 miles an hour, you will travel 9 metres as part of your thinking distance. That's before you've even applied the brakes, and it will then take a further 14 metres for the brakes to kick in, assuming that your brakes are in good condition, that the road is in good condition, and so that's a total of 23 metres, which means at 30 miles an hour, if someone steps out in front of you less than 23 metres away, there's nothing you're going to be able to do about it. At 50 miles an hour, the thinking distance is 15 metres. Not because it takes longer, but because your thinking distance is the same time, but you're travelling faster, so you travel a greater distance. And then the stopping distance is a further 38 metres. meaning that the total is 15 plus 38, which is 53 metres. So at 30 miles an hour, it only takes you 23 metres to stop. At 50 miles an hour, it takes 53 metres to stop. At 70 miles an hour, you will travel 21 metres just while you're thinking about what you're going to do, which is almost as far as the whole of the stopping distance for 30 miles an hour. And then it would take you a whopping, I'm not going to draw this to scale because it will go off the page, 75 metres in order to brake. And that gives you a total of 96 metres as your actual total stopping distance. Stopping distance, of course, is always a combination of the thinking distance and the braking distance. So what this shows is that at 30 miles an hour, you need 23 metres to stop. At 50 miles an hour, you need 53 metres to stop. At 70 miles an hour, you need 96 metres to stop. All of that assuming that you are sharp and on the ball and thinking fast, and that your brakes, the road surface, the tyres and weather are all in your favour. If they are not, those distances are increased. Back in this direction and slowing it down. So actually Newton's law is right. This car would indeed continue forever at a constant velocity were it not for friction. And if you go into outer space, well away from gravity, because gravity, as we shall see later, is also a force that will slow you down or speed you up, depending. If you get into outer space and you get your tennis ball and your racket and you serve the tennis ball at, 100 miles an hour? That tennis ball will continue at 100 miles an hour without any more input from you, right the way across the universe, forever. It will never slow down so long as it doesn't encounter any forces, and that might include gravitational forces, which would cause it to slow down or change direction. So Newton's law. If a body is at rest, it'll stay at rest unless acted on by a force, or if a body is moving, it will carry on moving unless it is acted on by an external force. And on Earth, we always observe that frictional forces, or air resistance, or whatever it may be, act as a force to slow us down. But if they weren't there, without any need for any more pushing, this car would just continue to travel forevermore, were it not for the fact that friction slows it down. So now we come to the second law of Newton, which can best be described by a formula, and I'll show you what the formula is. If you take a body of mass m and you give it a force, just like I hit the... Hello, today we're continuing in our series on GCSE Physics, looking at Newton's laws of motion. There are three laws. The first says that a body continues in its state of rest or uniform motion unless acted on by an external force. What does that mean? Well, that means that if you take a body, like a car, and you put it down at rest, it won't move unless a force acts on it. That sounds pretty plausible. If I want it to move, I've got to give it a force and then it will move. But the second part of that law is not quite so obvious, because what Newton says is that if you give that car a force, it will continue forever at a constant velocity. But of course, all of our experience tells us that that is precisely what it doesn't do. If I give it a force, it stops. If I roll a ball along the ground, sooner or later, it stops. How is it then that Newton thinks that if I give it a force, it will carry on forever? Well, Newton doesn't say it will carry on forever. It says it will carry on at a constant velocity unless acted on by an external force. And of course, it is acted on by an external force because as this car goes across the cloth, friction is acting between the wheels and the cloth. And that friction is a force. It's a force which is slowing the car down. Friction always opposes motion. So if the car is going in this direction, friction is pointing the car has a mass m, I give it a whack, that is a force F, then Newton's second law can be written in this form, F equals ma. In other words, a is the acceleration, just as it was in the first video that we did. If you take a mass, you give it a force, it will accelerate, and it will accelerate for as long as the force applies. If you take the force away, then of course there's no longer any force, so there won't be any acceleration, and consequently Newton's first law now applies. A body will continue at the velocity it was for as long as you like until it's acted on by another force. So if you give a mass a force, that will accelerate it.